the second Friday, fourth Friday meeting of the OHDSI Phenotype Development and Evaluation Workgroup. Today is April 28th. Just quickly, the workgroup's OKR. Objective 1 is to harden the phenotype development evaluation framework. We tried out, we tested the framework in the OHDSI Phenotype February by helping the community complete 10 phenotypes. I still give it a check mark. I think we met that group, that agenda. We still have work to do to complete it. So we do want to enable the community to convert those work into scientific peer-reviewed publications. So we'll talk about that topic. But I think we're still doing well for this OKR. We do have certain items that I have marked as yellow. The terminology and scientific definitions of what we do is still ambiguous. So we said that we want to clarify the terminology and scientific definitions and deliver a document that organizes such ideas with the timeline of Q2 2023. I think that we are not doing well there. We have not started that work. It's a challenging work, but we need to somehow think about how to make progress there. We are one of the main one of the things that a lot of people have expressed interest is to convert the work that we're doing into scientific peer-reviewed publications. So we are making progress here. There's a paper that is in the that I'm leading, which is the paper that's on Cohort Diagnostics that has been submitted to the JAMIA and is under peer review. So that has made progress. I will hopefully, if I get some time, I'll put it in medRxiv and make it available. There are many other work that we have proposed, and we need to talk about that. In terms of the OHDSI Phenotype Library, the OHDSI Phenotype Library continues to receive submissions. We have a large body of submitted phenotypes that have not completed peer reviews. So we need to think about a framework to accelerate the peer review process. In our last call, Maxime Moynard presented his work to this work group, and the work group accepted the definition and is now in the Phenotype Library. I'm thinking a simple presentation by the contributor to the work group and collective review would be sufficient for acceptance into the Phenotype Library. But we still have to test that out a little bit more. So those are the high-level ideas that this work group is working on. Any discussions on this work group's OKR as of right now? Okay. So let's go to the agenda. The main agenda item for today is the presentation from Juan Banda. Just to give a background on this. One of the OKRs of our work group is to integrate probabilistic phenotyping with rule-based phenotyping. That's the one that's marked in blue here. It's a Q3 2023 deliverable. Juan Banda is leading this conversation. We've had discussions on this in 3 different work group meetings. Juan has offered to lead a subgroup, which is currently proposed to be named Beyond Rule-Based Phenotyping. We still have to determine the meeting frequency, the sub-team, and the resource that is needed to support this work group. But there was some conversations in the work group. Joel had said, expressed the unfamiliarity of the community with Aphrodite. How does the output look like? What type of cohort is being built? And Juan had offered that probabilistic phenotyping is now accepted and it's considered a mainstream idea. Evan wanted to had some further questions about how rule-based phenotyping could be improved by probabilistic phenotyping. So this types of conversations led to a request from the work group to Juan to make this presentation. So today we'll be hearing from Juan about his ideas on integrating probabilistic phenotyping and rule-based phenotyping. I think he'll start with just the idea of probabilistic phenotyping and give us some introductions to Aphrodite and then the broader idea. So Juan, if you're ready, please take it away.
Good to go. Let me just share my screen. No. Can everybody see this now? Okay. So yeah. So thank you for the introduction, Gowtham. So I'll give the brief introduction about what is probabilistic phenotyping, how it works, and how many steps you need to do to get this to work. And then I'll talk more about how this has been, integrated and played around with to further, the mission of this work group in general. So let's start with, yeah, there we go. So as we all know here, the standardized phenotyping in OHDSI is, traditional rule-based way of building phenotypes. So like PHKB, and you build them in Atlas. The new Phenotype Library contains a lot of them, and they're freely available, validated, and everything. So it's all good and fine as traditionalists. The only con of this is that they're rigid rule-based definitions. So if somebody's missing one of the codes, or if the definition requires 2 times of one code but they only have one, that person's out. But that missing piece could be because it's just incomplete data in DHR, right? And we're still leaving that person out, even though everything else in their record might say that he's 99% chance of that phenotype, but with these rule definitions, that person gets tossed out, and it might even go into your controls, right? So, it might cause some other downstream issues. So for doing probabilistic phenotyping, so Aphrodite is called, this is a name that Patrick Ryan came up with many years ago, but it stands for, automated phenotype routine for observational definition, identification, training, and evaluation. I need to catch a breath after saying that every time, but that's Aphrodite. And this is a framework that allows people to, do phenotyping via supervised or semi-supervised learning, using this concept of noisy learning. So here, basically, this works on CDM 5.3 and different versions of it, and older versions as well. And it combines 2 published phenotypes approaches, which one was called Express from Vibu Agarwal from Nigam Shah's group, and Anchor Learning from Yoni Halpern from David Sontag's group. So these 2 groups came up with this approach, very similar approach at the very similar time. I think we were racing to who published first, so that was fun back in the days. But the approaches are complementary; they're not necessarily the same, and I'll explain a little bit more about that. So here, the other point that we wanted to do is enable sharing and reproducibility of the phenotype recipes. So much like the Atlas definitions that you generate, Aphrodite, you have definitions here as well to share, where you can also share, the trained model that you're using, not only just the configuration and the keywords, which is the recipe. And I'll talk about some example we did where we try that in multiple sites. Yeah. So what is noisy labeling and weak supervision? So there's bigger hype now about this. And weak supervision means, using noise or imprecise sources to provide a supervision signal for labeling large amounts of training data. So here, ideally you find, for example, the most trivial example I can give is, you want to find people who are type 2 diabetes. Well, one single code of that, could give you enough signal to actually build a model, or to learn what those people look like, right? So we're not only depending on this heuristic or weak label, we're leveraging that to find a set of people, and then use machine learning to build a model with the features that all of them share in common, rather than so learning that from the data, not me sitting down with a bunch of clinicians saying, oh, well, they need to have a code of type 2 diabetes, they need to have this lab needs to be low. No. We just tell, okay, those are the people that we're interested in, and machine learning figures out, the set of patterns or the features that they all have in common. So here, we use by adopting these heuristics and defining these labeling functions, we label a data set, and this data set is called a silver standard data set, which is easily and is programmatically generated, and it's very easy to generate. I'll show you, at least in Aphrodite, you just need a keyword. You don't need anything else, and the keyword could be in the notes or it could be a code. Either way works. And, in general, this heuristics should have, high positive predictive value to be useful, right? I mean, so if I want to find, the type 2 diabetes people, the type 2 diabetes term, it's probably the best one. But, I mean, because otherwise, if you use like, oh, somebody on metformin, well, that could mean many other things, right? So you want to have this high positive predictive value from the feature or labeling heuristic that you're using. So how do we know this works? Well, we did an evaluation a few years back where, we selected phenotypes from eMERGE. We selected phenotypes from, the OMOP set for myocardial infarction and type 2 diabetes. So the way we did this is, okay, so fine. We did the phenotype selection using those rule-based cohorts. We identified a set of patients. People did chart review. We used the software using just the myocardial infarction keyword or just the type 2 diabetes keyword, and let that find, let's see if it finds the cases and controls and how does it do, based on the chart review. So what, we show that we have very similar performance, as you can see, for both myocardial infarction and type 2 diabetes to somebody chart reviewing or, using the rule-based definitions. The paper has a lot more of the details. I summarized a 12-page paper in like 4 sentences. So if you're interested in how that goes, the paper has a lot more details on that. So how does the pipeline work? Well, it's a very simple pipeline. You have basically 5 pieces to it, and each one is very clearly defined. This is an R package. It used to be a Python package that didn't work with OMOP. I turned it into an R package that works with CDM at least 5.3. And your steps are, I'll go through them each by one, but this is just, the overview. So the first step, step 0, you need to configure. So you need to point this to, to your instance, password, everything, how many cases, how many controls you want, just naming stuff, and what kind of domains do you want to look at. So this Aphrodite allows you to, use only drug exposures, conditions, procedures, observations, visits, or any combination of them, depending on what your data has, right? So if you have a registry that doesn't have a certain piece of a certain data domain, you can turn it on or off. I mean, well, if you turn it on and you don't have data, it won't say anything. It just don't find anybody. But you can just turn it on and off, and you can actually see, what kind of data domain, how much does that contribute to your phenotype definitions. Additionally, this is one of the few packages that uses the notes NLP table. So if you have any extractions done, on your node NLP table, and you have concepts tagged and ready there, this package also goes and looks for the heuristic in that list. One important thing, this is the heuristic name or the labeling signal that I'm giving it. So basically, I want to find everybody that has something in their record that a term or a note mention of myocardial infarction. This term could be anything, any of these domains you can use a term for. So you can use a term for a drug, you can use a term for a procedure, or you can just use a diagnosis code or whatever thing you have in the notes NLP. And we have a very interesting study that we did where we were looking at familial hypercholesterolemia a couple of years back before there was an ICD code for it. So that was useful because we were able to find the mention in the notes NLP table rather than, depending on the code that didn't exist up until a couple of years. Okay, so first step. So you build your keyword list. So here, remember, we have this myocardial infarction term. Aphrodite automatically goes and fetches the vocabulary and everything that has myocardial infarction in it, and that's part of the vocabulary, either children. I think up in one level up could be mentioned as well, and one and two and multiple levels down as children of that concept. So you'll find all these concepts. Obviously, we're not looking at free text. This is one big misconception. Everything needs to be tagged and annotated into OHDSI concept IDs, right? Free text, this does not look into at yet. So you get this huge list. You're able to curate it. So you can review it. This is part of the semi-supervised part where you see the list and you're like, well, I don't want number 2, 3, 4, and you just delete those rows. And that way, after you narrow down your definition, because you will have something very generic, or you might have something, very high level that might, render your cohort pretty useless. Or if you want to go pretty precise, you can just remove everything but the actual concept that you're looking for. So this keyword list is basically a set of suggestions, of what's in the vocabulary that could be on the data that you're running this on. This runs with one single function call, and it's down here. So now that we have this set of keywords, we use that to find cases and controls. So here, you find all the cases, meaning that somebody that, in their data domains has one of those codes. They're considered cases. Controls is people that don't. So again, this is a rather simplistic, a little bit more simplistic than your traditional, cohort definition, and we're not using precisely negative controls or anything like that. We're just saying, okay, you have any of the codes in that list, you're potentially a case. You don't have any of the codes in the list, you could be a control. That's it. And that's also done, in two different, one function call. It takes a bit to run. And after that, you have your cohort. Now we can actually go and find, your data for the cases and data for controls, so we can actually make, build a machine learning model. One key feature here is that, well, we all know that those people that we selected are cases and controls have been picked with a set of codes. So if we leave those codes in there, what is the machine learning model going to learn? Well, the pattern of codes, right? So we take that code out for building the machine learning model. Why? Because we want to learn what the pattern is around that code, not just that code, right? Otherwise, you will have a very trivial classification problem where, you would be training on just people with one code, and then you won't, the classifier will most likely just going to pick that as the top feature since it's the, the top of the common feature. So we block out that code. So that's what this is saying. You get data, separately from the cases and the controls. And here's where, I see some people thinking you can plug in, a previous definition. You can plug in different things. You can mess with the cohort if you wanted to. So, it's very modular in the sense that allows you to, do stuff around what's supposed to be doing as well. After that, it just creates this feature vector where it basically takes all the patient data, creates this big matrix. There's multiple ways of collapsing time. You use frequency counts. You can use presence absence. You have different normalization parameters. So this builds a big feature matrix, and that's it. A very large feature matrix that's very sparse. We tried plugging in here, the traditional OHDSI featurization code from PLP and other packages. But, so that's a feature that could be turned on in Aphrodite, but we decided to keep it our traditional, the way that we were doing it at Stanford, to just create this matrix. However, you're free to basically plug and play with other functionality. After that, you have this huge matrix. Well, now you can train a model. And if you notice, all the calls are fairly clear. Everything is very well, very modularized in a way that you can do all this in very few steps. You build the model. By default, it's set up to do random forest. Oh, logistic regression, sorry. You can do random forest. You can do any model that could be run in R. So basically, I'm leveraging the package Carrot. And Carrot provides an interface for pretty much everything in the kitchen sink. So you can try anything that Carrot can use. and you can set up, what is your full cross validation, any of those parameters that you can set them here as well. Once you have a model, then you get an evaluation. Obviously, it takes a unseen set to be able to do that. You can specify, what is your training set and your test set, and this is, just the classifier report. So again, there's nothing on how well you're able to separate, your selected patients or cases and controls, basically. And you get this evaluation result, and you have the model. So now, you have the model, you can tweak it, you can get, whatever you want. You can compare that model against the gold standard if you have. You can do, you can evaluate it in many different ways. Here you can share, the code. So if you see this, the code set for this is probably 15 lines of code, after you get your tweaks. So you can share the code to another site and the other site can just run it seamlessly. You can share the model. So this produces a binary object for the carrot model. You can also share it to run it in another site. Obviously, this might have this is shown to be less effective than just sharing the code. Why? Because, coding practices at different places, different logic decisions done when people are doing ETLs. So, but that's the same problems we have when we're running Atlas phenotype definitions, right? I mean, some codes might not be present on other sites. So we did a study a few years back as well of, okay, so we shared both the model and the code, and how does this work? I mean, which one is better? So we did it with Colombia. We also tried it with, I think, some of the South Korean partners. And we showed that, yes, I mean, obviously sharing the model wasn't too bad, but sharing the code was better. We didn't need to tweak anything, but, I mean, we just tested it. Obviously, if you want to improve, your accuracy or precision recall, whatever you're shooting for in your models for your condition at your site, you might want to tweak a few things, but this could be shared fairly easily. And the performance, varies by not too much. So that was, a good study to look at. I mean, again, I summarized the paper, but you can go and look at, this reference for more details. So one thing that I noticed here, so all of this was in a vacuum, right? I mentioned Atlas here and there, but I never really said, okay, if we can compare both of them or if we can merge them. So this is a question that we had for last year's Phenotype February, and we did one evaluation of, of doing this for depression, I think. Yes. Depression. So we ran this at Stanford. We did, rule-based with an Atlas definition. We compared it against, the probabilistic definition, and we wanted to identify and characterize those cohorts. So we wanted just to do descriptive statistics, and then, train a model to evaluate a cohort. So how do we did this? So, okay, so we have here the overlap of people found by Aphrodite and an Atlas definition. So as you can see, for a weak definition, we just use depression as the heuristic or keyword. We get 50% of the same people as, an Atlas definition that somebody spent a couple of days or weeks figuring out. Okay, fine. That's not that hard to achieve, I guess. We do get, a good amount of patients that are, only in the Atlas definition. So that's also an interesting thing to note. And we get a good amount of patients, another 25% of people that are only in Aphrodite that could be missed by Atlas, right? So here the analysis that we wanted to do is actually we wanted to see if any of the people on this side, should have been picked up by the rule-based definition. Because those are the people that you're always going to miss with a rule-based definition. With a probabilistic, you can probably tweak it enough that you'll get these people, but a rule-based definition, you don't want to tweak because you already agreed to it. There's some sort of community and clinical understanding behind it. But our probabilistic one, you have a little bit more of a leeway. Why? Because I could just change my heuristic to include more terms. So the cohort is very similar, just the description, I mean, so we're picking the right type of people. Here, when the theory that we had here is that, or the hypothesis, we wanted to see if combining multiple approaches could result in more accurate and clinical meaningful depression cohorts, right? So if we, and that's, something that we set out to do, but we still, find comparable performance. What is the point that we stopped in this study is that we to look at the top features and we wanted to blend them into the Atlas cohort. However, we kind of stopped there due to lack of people time. However, we just comparing them, we're showing that our cohorts are very similar, even though we're missing chunks from people from both sites. The models built with whatever is intersecting are still pretty good. In terms of features of importance, you see that in Atlas. So the Atlas definition, rule-based definitions on the left. So those are the more important features. Again, we use the Atlas definition to find the patients, and then we build the model. We use the Aphrodite definition to find the patients, and then we build the model. And this is how we're comparing the features. I think I forgot to mention that. Yeah, so we have 78 to 80% overlap on the most important features. And the deltas here is what we're interested in, blending into either an Atlas definition, like for example, this stuff that was found, in Aphrodite, putting it here, or we could enhance the heuristic of Aphrodite by whatever selected definitions found on the Atlas cohort. We still didn't push this forward, but there's a lot of interesting open questions on that, and that we wanted to explore, and maybe as a subgroup here we could push that, because I think that there is value. We had some clinicians kind of look at it, but we didn't spend too much time in it, saying, hey, maybe this whatever code, this code might have been a good addition to the rule base or not, so that is the type of people we need to be able to do this. Otherwise, as computer scientists, which was most of the people that did this evaluation, we have no idea. Anyways, so yeah, so we have some interesting things that we could use, to leverage and improve both sides. Yeah, so here our conclusion was that, the probabilistic depression cohort performs similar to the rule-based cohort. Combining the rule-based and probabilistic methods can identify patients that would have otherwise been excluded, that's for sure. We saw those deltas on the sides. Obviously, limitations, we assess sensitivity, but not specificity. We ran the experiments in a single EHR and a single phenotype. And we only did, 2 computational phenotyping algorithms, so we could do something else. We wanted to, incorporate domain expert review for the concept sets to be able to add. And this manuscript is still in progress after 14 months. Man, I need to really put this up in my list. So, yeah. So who has a better understanding of this? Who says, yeah, this is just hocus pocus, or who wants to, talk a little bit more about it? I see Christian gesturing with the hocus pocus part. So I guess, do you think that's the case?
How do I switch?
Okay, so this Christian, your hand is raised, so you get the first go.
How do I do it? Ah, here you go. I don't often raise the hand. I just start usually just bloat out. Actually, a couple of questions, Juan. Question number 1: can you go back to the slide where you compare the Atlas and the probabilistic one? This is stop. Way too far. No. The ones where you compare the individual criteria.
Concepts, covariates.
The top features, yes.
This is proteins, mean corpuscular hemoglobin. I think the left one is anemia or something. It is not. I think you put the wrong table there.
No.
Hematocrit.
No, this is just what came up with, as feature number 14. But that, after a few features, this thing's just kind of even out. Yeah.
So clarification, are these features as part of the features found on in the persons identified in the cohort? That is the characterization of that cohort, or are these criteria that were used to as part of the rule-based phenotype definition?
No. So we use the rule-based definition to find a cohort, right? And then we built a machine learning model from that cohort. And these are the top features. Well, that they're ranked here, but they're the ones that appear on the top that are non-overlapping for that cohort. Yes. Did I made it worse?
Yeah. This looks like anemia to me, but now you're saying it's rank, so there must be like all these wonderful. So where's 1 to 14?
They overlapped.
Oh, they overlap. These are the differences. Now
Yes.
I got it. So the automatic one didn't pick up the mood diseases and that kind of thing. It picked up, for some reason, other stray cats and dogs like protein, serum plasma.
Yeah.
Okay, good. Understand. And we expect that, right?
Yes, exactly.
We expect things to be picked up that we didn't think of, because that's the whole point. Okay, so question number 2. Does the model include the codes that went into the initial noisy, whatever we call it, starting cohort? Or can they also contribute? I mean, can they contribute, or are they excluded?
So traditionally, they're excluded. For this comparison, we just left them there.
No. I mean, so for example, you're looking here for depression. So I assume your Atlas cohort definition has depression as one of the criteria. Okay, probably. Does it?
Yeah.
I guess. Do I have to take that thing out, or does the tool take that thing actively out and says, no, I'm going to find these patients without those given to me initial codes? Or does it keep that and say, all right, well, obviously these are the right codes, so let me refine this a little. Which one is it?
So that's a great question. So when you're doing your analysis, you want to keep the codes out, right? Because that way it will allow you to find what's around them. However, once you're going to deploy your model to actually classify people, you want to put them back in.
Okay.
Yeah.
So I have to do that in the configuration.
Automatically it does it.
Okay,
so once you said, I'm good with this model, then it just takes it out. I mean, the feature set, it puts them back into the feature set. Yes.
Okay, good. Okay.
And then it uses those when it determines when it does the test set.
Yes.
Okay, so it doesn't use them in the training set, but it uses them in the test set. Okay.
I see. Okay. Well, so here's the thing, right? The problem is that what you do in Atlas is you create these differentiating criteria with a purpose. And, Gowtham has heard that sermon many times, that the purpose should be explicit rather than implicit. But you do that, right? So you're saying, but not type 1 diabetes, okay? It's very important for you that type 1 diabetes, even though the covariate space probably massively overlapping, that it draws a very nice line. So you almost want to use some boosting methods to actually distinguish them. You do that in Atlas, again, implicitly, so it's in your head, right? You're saying, that one I don't want. The model doesn't know that, right? It just randomly kicks out. Or can you tell it? Can you actually give it a gradient saying, not that one? Make sure that you don't get those guys. Can you do that?
So exactly. So we have an inclusion and an exclusion heuristic.
Okay.
I just mentioned the inclusion heuristic, but you can also add a code of not this. Yeah, because you're right. I mean, you want to delineate right one condition from the other. Yes.
Okay, no, that's good. That's very good.
So please say it again. So you can actually put in your model, don't use this?
Well, and your heuristic, yes.
in your heuristic. Okay. Well,
In-
yeah, that's what we do in Atlas. You're talking about.
Well, in
No.
Aphrodite as well.
Oh, okay.
So
I
I
guess
could
I'm
say I
confused now.
want-
What's the heuristic portion of Aphrodite?
When you build your keyword, right? So my keyword list is myocardial infarction, or at least or for type 2 diabetes, and I can have an ignore list of type 1 diabetes and whatever codes related to it. Yeah, I kind of didn't explain that part well.
Okay, so it's an ignore list and not a. So if
avoid-
somebody has type 1 diabetes, that you ignore them, they don't get, minus points, negative points for something.
Yeah, they just
for
don't make the cases cohort. Yes.
They could make.
So you actively avoid those guys, or you just say that one, don't use it.
Well, again, you can do both.
Okay, good. You can do both.
Yeah.
So now
going
that
to your
go
going to
ahead.
example, Christian, like the inclusion rules that we have in Atlas, if you think about it, entry event criteria, that's the top portion of Atlas, can be considered as in it to bring a lot of people in, maximize sensitivity. And then if you add inclusion rules, you're improving specificity by removing people that may not be eligible. So enter all people with type 2 diabetes or all people with diabetes, remove people with type 1 diabetes. That way you're improving the specificity of type 2. This example, though, is more about improving sensitivity. And it's all about finding people who may have type 2 diabetes and is missed by the rule-based phenotype.
Well,
So
because
that
you get a probability here, right?
it doesn't really care about the specificity, at least in this example.
Okay.
Gowtham, yeah, of course. That in Atlas you do that, and that's why I'm asking whether or not you can do a similar thing on the other side, on the Aphrodite side. Okay, so here's the question, Juan. How well? So what you do is you use the criteria given to you, and then you're saying, well, the data knows more because there are connections between these covariates which are not explicit, but I can find them through training. And then I can, if I combine these with the ones which you gave me, the result's going to be better. That's the premise. And same as in Atlas, right? The inclusion criteria increase the quality, improve the quality, either sensitivity-wise or specificity-wise or timing-wise of the indexing criterion.
Well, yeah, but the thing, with Atlas is that you will never be able to get somebody that's 90% any phenotype, right? Unless you add,
Yep.
very specific rules for that.
Yes, you're right.
Yeah.
But here's the but. How well do you know what the other data know about this stuff? Okay. So it could be that there's a condition that you're looking for, and really there's not much to it. There's no treatment for it, and there's no surgery, and there's not much in the way of diagnostics, things like this, right? So take depression if before 1956 and you didn't have antidepressants, okay? What are you gonna do with that patient? Nothing, okay? Give them a sleeping tablet. Very unspecific. So there, I would state the other data are clueless. They don't help. And then, of course, there are other situations where it's all over. It completely changes your life, and it certainly changes your medical life, and everything is different, and a ton of stuff happens, right? The healthcare goes wild. I don't know, some chronic immune disease, right? In irritable bowel disease or lupus, right, has like already 7 different symptoms to begin with, and then a whole lot of other things which are funny. So the data is going to be like a whole choir, a church choir. A whole lot of other things are going to be kicked off. And yeah, in Atlas, you're not going to get that. You're not going to, nobody builds Atlas the phenotypes that are longer than, let's say, a dozen criteria, because at some point you just, you have enough.
Yeah.
But you can do whatever you want, and they're all probabilistic, so they should be better. How do you distinguish? How do you know? How do I know that probabilistic model using data that the system finds itself actually adds a lot of value? In both sensitivity is probably easier because you can do case validation, but of course, the false negatives are harder. What do you do with the false negatives? So how do you know that? How do you know you're on the right track here?
Well,
Could
I
I-
mean,
Could I speak to it a bit?
yeah, go for it, Chris. Up.
So sorry, I've been driving here, guys, and had my hand up for a little while. The issue that you bring up of how do you know? There's some techniques to try to estimate the fraction or the probability in a calibrated way that someone has the phenotype. It does rely on a couple key assumptions. And the one that we sort of can't do anything about is one of separability. So if you have two people with the exact same covariates that have two different ground truths, you have a problem. So that issue where there's just no signs or symptoms for something that would ever be recorded for a condition, you just can't do much. But to the extent there are some signs and symptoms, we can do better and better. I put a link to some of the OHDSI and a new preprint of ours on a technique that also gets to your other question. So positive unlabeled learning, you can think of it as take the phenotypes for which your rules-based technique has coded stuff that you could say, yeah, those are real positives, right? And as Juan said, you take out the covariates when you're building your model that are basically saying that those are positive. That positive set is then differentiated from the rest that don't have any of those characteristics that you say make it that phenotype.
Yep.
And then you can probabilistically estimate the rest of them, what their chances are they have the phenotype. And that was that part of his Venn diagram. It's been there's a literature on this for 15 years of trying to estimate and calibrate that stuff. We've just made some advances, but and what we're seeing in certain fields like mental health is the fraction that is uncoded or undiagnosed can be very large. And so that's where I really wanted to bring the discussion that you can get a beautiful rules-based phenotype for, say, self-harm and only capture 1/5 to 1/8 of the people with self-harming behavior. Right. And there's where you have a potential with probabilistic phenotypes to increase your power because you can now detect and calibrate the chances that person has it. So some people have 2%, some people have 98%. You don't necessarily even have to pick a hard and fast cutoff of 50%, but you can use those phenotypes within your comparative effectiveness and other studies. So that's kind of what I wanted to say.
Sort of going along with Christoph's point about bringing it top probabilistic. I mean, that's one. What you get a probability of the person having the disease, depression, myocardial infarction. What do you have? What do you use? Do you use cutoffs, or do you use the probability and say this person is? How do you do it?
Well, that depends on what application you want to use. So, or what do you want to use this classification? But usually, I mean, we done cutoffs, right? Because we basically compare it against the gold standard, and with the gold standard, we develop a cutoff to say, okay, up until this, percentage probability, you get most of them right.
So it's a your cutoff is what, condition dependent or phenotype dependent?
Yes, yeah, definitely.
And you compare it to, you said you compare it to your gold standard.
Yeah, so the paper on FH that we have, we did exactly that. Yes.
Okay.
I would add that you can do a sensitivity analysis over a range of cutoffs. We did a comparative effectiveness study that way on self-harm. And the other thing is, if you have a way of testing patients, so say to go beyond a chart review where you're actually bringing in patients, confirming them, you can take your probabilistic model across a properly selected set, usually selecting people over the range of probabilities, and you can actually calibrate your model from known negatives and known positives. So the trick is the chart. We call it a gold standard, but in many cases it's not even complete. But if you can bring in 100 to 200 people for a condition, get them tested with lab tests, do the full workup, and get even better ground truth, you can go beyond chart review, and then have a calibrated machine learning model that reflects ground truth more accurately.
Okay, so we have 8 minutes in the work group. The purpose behind the presentation that Juan gave us is obviously to educate us, but also to kind of a call for action. Do we want to work as a subgroup to advance this further under the leadership of Juan? Is there an interest for a subgroup? And if yes, we can talk about what the subgroup can do for the next 5 minutes, maybe.
I'd certainly be very interested in working in a subgroup. I think we need to get past heuristic phenotyping. It's there's definitely issues with, while it's fast and it's easy to understand, its accuracy is wanting, especially in a lot of cases. And I think that probabilistic phenotyping will certainly help. So I think it's an interesting idea to have some sort of combination of probabilistic and heuristic phenotyping, and I think that would be a way to something to explore.
Okay. Anybody else interested in the subgroup?
I'm very interested in it. Just got bandwidth issues.
Yeah. Maybe
our code to this.
Yeah. What do we think we can tackle in the short term that can bring value to the partners and also best use of time? One idea that I'm gonna throw out is Juan said we need to finish up the work from 2022. Is that something that could be used?
Yes, that's exactly what I was going to mention, right? I mean, doing it, some sort of end-to-end in that regard, so we can know if there's a value of, adding those features into the rule base, or if we do a hybrid to, get to the people we have to. That's, I think that was my biggest interest in, pursuing that part.
So what would that entail, Juan?
Well, first of all, I need somebody that could run this, because the data that I had access to is gone now. So we need to run this somewhere else. And and we'll need, one or two, some people with clinical expertise that could say, okay, this feature might be good. Like Christian said, right? Oh, this ones are crap. Well, we need somebody to say that, and also say which ones might be worth adding or, considering.
Okay. So if I set up a meeting that involves some of us, Christian, Christoph, would you be interested in joining if we find time? Joel, me, just to talk through the idea of completing the 2022 work and learning from it.
Let me see what I can find. Yeah, it's a bandwidth thing, as Chris said. Let me see what I can drum up some interest. Yeah.
Okay.
I would add that there's an effort in the mental health working group of OHDSI to look at phenotyping with NLP and also using machine learning. So there might be a complementary possibility. Andrew is leading that one.
Sure. I mean, the application that we were looking at is depression, so that would work fairly well with that group as well.
Could we reach out to that group and make a presentation there or drum up interest there?
Yeah, I'll reach out to Andrew.
Okay, cool. Juan, do you want to talk about next steps after this call, or like coordinate with this smaller group?
Yeah, I'll coordinate directly. I mean, and now I don't think so, but yeah, I mean, I'll set up kind of an agenda of what needs to be done to complete that part, and then let's see what people how they want to take it as well, because I mean, there might be things that I'm not considering that might be more interesting.
Yeah. And in terms of your ask about data partners, I think we can arrange that, some support there.
Awesome.
Okay. Great. So that's the main agenda for today's work group call. Now, I'm looking at the attendee list right now. So people are leaving. It's almost time. So I think we can close the meeting. I'm going to stop the recording, unless anybody else has any other topic they want to discuss right now.
It was something that I wanted to bring up, but I'll just leave you here for a couple of weeks. Let me just get to my slide. I wanted to get some people involved in this work that I'm doing. So I'm doing it from two sides. I'm doing it from one side on, fully doing automatic phenotyping using ChatGPT or GPT-4, whatever. So I'm already working with some people on, going all the way to codes automatically from ChatGPT, which is I think it's doomed to fail. But more, I'm more interested in having people, if people are interested in qualitatively evaluate, if we can use, LLMs or ChatGPT-4 to speed up the gathering of information and, the getting a definition rather than, spending weeks and months looking at papers, doing lit reviews, using these things, GPT-4 to do it for us. And how good is that? Because that also helps. I mean, that other part that I wanted to work with in this group is, scaling up, the rule-based definition, the definition building. And with LLMs, I mean, I have some examples. I'll show them next time if I get some minutes, but it's pretty okay. We just need to, qualitatively evaluate if, this is something that it's all the time okay.
That's very interesting.
I have an interest in this topic, but I do have, but I cannot discuss that in a recorded session. But how to use ChatGPT for phenotyping.
Okay, so I mean, if you want to, I'll just shoot out an email and we can I mean, with what I want to do here, and maybe we're overlapping because I'm pretty sure that I'm not the only one with the same idea. I haven't seen it out there yet, but it's bound to happen. So maybe we are going the same direction. We just don't want. I mean, the reason I was going to put it out here is because I'm in the point that I have everything that I need to do except somebody with clinical expertise to evaluate whatever's coming out of GPT-4.
So yeah, so if anybody's interested in this particular topic, please reach out to Juan. Juan, if you are talking to the community, please invite me. I'm interested in this topic too. Would like to participate.
Sounds good. I'll get a thread going. Well, an email going first.
Yeah, Juan, if you can include me too, as Joel.
Awesome. Yeah, I don't want to, we don't want to get scooped too quick.
And Christoph just messaged saying he's interested.
Oh, awesome. I'll add him as well.
Okay, great. I'm going to stop recording now.
Sounds good.
This concludes the formal session.
Awesome.